Now, the whole reason that we looked at conic sections through the eccentricity and directrix approach was so that we could work with polar equations for conic sections. Now, this is the first time that we are not starting with a center or a vertex of our conic section on the origin. We're starting this time with the focus on the origin, and that's a very, very important difference. When you're working with polar equations, you're not going to be able to use the relationships between eccentricity and directrix, the value of E and D, to get all the equations for all the directrix lines and all the ordered pairs for the foci. So just be aware of that. So this is a little bit different, but we have to start with a focus on the origin, or else we can't work with conic sections at all. Alright, so let's see what we can do here. We're going to start with a parabola because that's the most simple conic section. So here's our y-axis, here's the x-axis, and we have a focus, or the focus will be on the origin. The directrix is a line, well, it depends. You could have a directrix that crosses the y-axis. You could have a directrix that's crossing the x-axis. We're going to start with a directrix crossing the y-axis. No, that's the x-axis. So we're starting with this as our directrix. Okay, and this directrix is perpendicular to the x-axis, and it goes through the point D0. The focus is the point 0, 0. Now, for a parabola, you'll remember that the vertex must be right between the focus and the directrix. And then our parabola is going to curve around the focus and kind of away from the directrix. So our parabola might look like that. This time, when we pick a point P on our parabola, it has coordinates r theta, because we're working in polar coordinates. And the distance from P to F will be the directed distance r. Of course, this would be the angle theta, the angle made with the x-axis there. The distance from P to the directrix is still going to be PL. So we're still talking about a perpendicular distance there. That's L. Okay. Alright, and absolute value of PF over absolute value PL has to equal the eccentricity. Okay, and again, P is the point r theta. So let's see. The distance PF is r. The distance from P to L, that's what we need to kind of think about right now. Well, that would be, if you measure from the y-axis out to the point L, that would be d units. Okay, but we're not actually going to be measuring this distance right here. So here's what I'm going to do. I'm going to drop an altitude from P down to the x-axis. And this x value here, this distance along the x-axis, is what we have to take away from the entire distance d. So absolute value of PL has to equal has to equal d minus x. The length d minus whatever x is. Now, but we're working in polar coordinates. Remember that in polar coordinates, x is equivalent to r times the cosine of theta. So the absolute value PL, absolute value of the distance PL, would have to be d minus r cosine theta. Okay, so absolute value of PF divided by absolute value PL must equal r divided by d minus r cosine theta. And that's equal to the eccentricity e, to the value e. Now if I take this equation and solve for r, okay, I'll leave the steps to you, but you will get r is equal to ed over 1 plus e times the cosine of theta. You need to make sure that you can do that math, but this is the polar form for the equation of a parabola with a focus at 0, 0 and a directrix at x equals positive d. Now, certainly we know we can have a parabola that opens the other direction. So that the first parabola we looked at opened to the right, no, to the left. We also want to take a look at what happens if we have a parabola opening to the right. So the directrix would be at x equals negative d. Okay, there's my parabola. We're still looking for the distance from P to F over the distance from P to L to be equal to the eccentricity E. So if I pick a point P, remember that P has coordinates r, theta. This is the value r. This is the angle theta. Okay, and we're going to need that drop down. Okay, what am I missing? I need to show the distance from P to L. P to L would be right here. Okay, P to F is r. The distance from P to L, which is marked by this dotted red line, would be, okay, we're talking about a distance. The distance from the y-axis back to this line is x units. Excuse me, is d units. But we want to not count this part, which is r cosine theta. So let me think about, yeah, all right, so we need to subtract r cosine theta. So that's going to be d minus r cosine theta. If that is equal to E, hang on, all right, correction, this should be d plus r times the cosine of theta. Now, let's think about that there, because that bothers me a little bit. Basically, d is measured in a negative direction, so if I add something to this negative number, then I'm going to be taking it away, basically. So because if we're thinking about measuring from the y-axis back to the line, that would actually be a direct direction of negative d. So negative d plus r cosine theta would give you this distance. Then the absolute value, this is all going to work out. Solve this for r. Boy, that was painful. Don't think about that too much. Solve this for r and you get ed times 1 minus e cosine theta. Okay, parabolas can open upward or downward as well. So let's see. Focus at the origin. So let's let our directrix be a horizontal line above the origin. So that line is y equals d, and that's not exactly the right place. The vertex of our parabola is going to be halfway in between the focus and directrix. So our parabola will look something like this. That's really bad, but it's going to be good enough. Okay, we're going to need a point on our parabola. So let me put the point here. There's point P. Point P is r theta. And we're going to need to talk about the distance from from P to F and from P to L. So P to F is here, P to L is there, and we can kind of see how bad my parabola is off. Those distances should be the same. The distance from P to F, of course, is r. The distance from P to L this time is going to be d minus this y value in this little right triangle. And y is r times the sine of theta. So when we look at the absolute value PF over the absolute value PL equal to E, we're looking at r over d minus r sine theta equal to E. Solve that for r, and you're going to get ED over 1 plus E sine theta. If the directrix is below the origin, so that would be the equation y equals negative d. D is a distance now. So negative d just tells us where it's located. The focus, of course, is here. The vertex would be about here, and our parabola curves around this way. Ouch. Banged my elbow. Pick a point P. We're looking at PF, PL, so PF over PL. PF is R. PL is going to be D plus R sine theta. And solving that equation for R, because all polar equations have to be solved for R. Solving that equation for R, you'll get ED over 1 minus E sine theta. Alright, interrupted one more time by the phone. Alright, where was I? Okay, we've been looking at polar equations for parabolas, and I started with parabolas because those were easy to draw and easy to explain. We can summarize all of this for all conic sections. In fact, the equations aren't going to look any different. What we do is we're going to let, that's a T, about D be some positive number. Okay, a conic section with a focus at 0, 0. And the conic section may have another focus, it may not. If it's a hyperbola or an ellipse, there will be a second focus that you've got to find. Alright, so conic section with a focus at 0, 0, eccentricity of E has a polar equation. R equals ED over 1 plus E cosine theta, or r is equal to ED over 1 minus E cosine theta. When cosine is in the equation, one of the directrix lines would be, okay, and it's one directrix. It might be the only one, it might be one of two. One directrix at x equals d if you have a plus, and you have one directrix, I'm having a hard time, at x equals negative d if there's a minus in the equation. If the directrix is vertical, then you've got a conic section that curves away from that directrix. So that makes the foci and the vertices on the horizontal axis. The other option is you can have a conic section with polar equation ED over 1 plus E sine of theta. Or R is equal to ED over 1 minus E sine theta. If that's the case, then you're going to have a conic section that's vertical. The foci are on a vertical axis. It probably isn't the y-axis because it's a focus point that's on 0, 0 now. But we would have one directrix would have the equation y equals d. So we got horizontal lines now. So it's a plus, y is equal to positive d. If there's a minus in the equation, you have a directrix at y equals the opposite of d. So d is a distance, it's always positive. We just make it have an opposite negative value when we need the line to be below the x-axis or to the left of the y-axis. So these four equations will do for any conic section. It's just going to depend on the value of E, whether you have a hyperbola, an ellipse, or a parabola.